Show Engine InnoDB status. So the overview is basically Show Engine InnoDB status. We're going to go over it. Basically, it shows you the internal InnoDB status variables. We wish that you could just see it in the output of Show Global Status, but unfortunately you can't. You can see some of them in that, but not everything. And basically, in order to get the most value, you need to know how InnoDB works. So as we go through this, I'm going to be explaining kind of how InnoDB works on a, on a more internals kind of a level.
And the question is, do you distinguish between InnoDB or InnoDB plugin?
Do I distinguish between InnoDB and InnoDB plugin? No, right now I don't. I also don't distinguish between Percona. If you do Show Engine InnoDB status on a Percona build, there's a couple of extra things in there. We have a few clients who are using for the Percona build, and it is really good for higher performance. But there's some of them are different versions, and so I didn't want to take one version if the different version had different things. So this is just standard MySQL InnoDB. I would say 5.0 and 5.1 this is good for. And most of 4.0 and 4.1, which is 4.0 is InnoDB was introduced. There may be some things that aren't, but I haven't really researched to look and see if it's not. So it's called Show Engine InnoDB status. You can also say Show InnoDB status. That's going to be deprecated. So the first thing that you see is you see a header. And this header just says, what time is it? So this particular example of the header was taken from September 4th, 2009. So 09/09/04. It starts with the year 09, and then September 04 at 9:36 local server time in the 9 a.m. in the morning. And it's InnoDB monitor output. It's actually called the InnoDB monitor. One thing that you can do is if you want to get the Show Engine InnoDB status output saved to the error log once every 15 seconds, I think it is, you can make a table in the MySQL database called InnoDB_monitor. Create table InnoDB monitor aint engine equals InnoDB, and then to stop the monitor, you do drop table InnoDB monitor. And so basically, that just tells MySQL, oh, it does say InnoDB, when switched on, InnoDB monitor prints data about every 15 seconds. Server output is usually directed to the error log. So if you, this is usually like a temporary thing. You don't usually leave it on, keep it on, leave it on, otherwise your error logs will be complete. So this says per second average is calculated from the last 12 seconds. Usually that number is no longer than about a minute or so. And you can't really control it, so it's just for informational purposes that when they get averages like blah per second, that's just, it's not amortized over everything, it's just over the last 12 seconds. As opposed to like show, if you do Show Global Status, you get numbers, and you usually end up dividing that by the uptime, or uptime since flush status, and then get the kind of per second. But if it's been up for a week and a half, that's a very big average to take from. So the next section is actually on semaphores, but before we go into a section on semaphores, I wanted to explain what semaphores are. And to do that, I had to figure out what semaphores were, because I was kind of like, they're kind of locking thingies. They're things that deal with locks. And so I went to Wikipedia, and Wikipedia says a semaphore is a protected variable or abstract data type which constitutes the class and method for restricting access to shared resources, such as shared memory and parallel programming. So basically, it's a method for restricting access to shared resources. So basically, it's a locking thingy. But, I had this section of like semaphores, and I'm like, I wonder what a semaphore is, Like, I kind of know what it is in sailing, but, so.
Isn't it just a fancy word for flag?
It is a fancy word for flag in sailing, yes. There you go. And in fact, here, it's a fancy word for a flag, too, because the flag is that you're locking it, right? So sometimes when you lock something, you might create like a temporary file that just says I've locked this PID or something. So semaphores. So this is where we're going to get into a little bit about how InnoDB works. So bear with me a little bit. InnoDB has basically a multi-phase wait policy when there's contention or locking. First, what it'll do is it'll try to use something that it calls a spin wait. And you can see these mutual exclusion spin weights. And so what this 0 means is that at the time I did Show Engine InnoDB status, there were no current mutex spinning. So there was nothing that was doing the mutex when I did show engine EODB status in the last 12 seconds. So basically, first what it will do is it'll do a spin wait, which eats up CPU cycles while it's waiting. And basically what it says is just, sleep over here in the foreground, not in the background. Sleep in the foreground, and then come back, and then we'll see if we can, we'll see if we can fit you in. We'll see if we can get this mutex lock thing solved. But right now we can't.
So in the loop it checks the state of the flag, and if it is still busy, it goes back, and so on and so on.
Right, and that's going to eat up CPU cycles because it's still in the foreground. And if the thread can proceed, great, and it just goes. If it can, it goes back and sits there. After a certain amount of times that it goes through this waiting, this loop basically, it will actually go to an OS wait, which basically means it will context switch. So it'll say, okay, now you're in the background. I'm going to do a context switch. I'm not going to worry about that. So spin waits are good because you don't have that overhead of context switching, the memory and all that kind of stuff. But they're worse because they use CPU cycles. So in general, an OS wait, which is what we talked about up here, is more expensive. And the reason that you have a lot of reservations is that, I don't know when it makes the reservation, but let's say it makes the reservation when there's only like 2 loops left for it to do. It might actually the process might actually get to go before it actually runs out of loops that it has to do. So you might have guessed that this variable down here, InnoDB sync spin loops. Now this is a status variable that you can set. It defaults to 20, and it's the manual actually says, I quoted from the manual in my notes, it says the number of times a thread waits for an InnoDB mutex to be freed before the thread is suspended, and that suspend is the OS wait. The default value is 20. It's a dynamic parameter, so you can set it, and it's a global parameter, and it's dynamic, so you can set it, if you need to change it, you can set it on the command line. Now, when do you set it? Well, it's really kind of a trade-off. How many spins do you have, spin weights do you have versus how many OS weights do you have? If you want to have more OS weights, you can reduce the number. If you want to have fewer OS weights and more spins, you can increase it. You can set it from 0 to 4,294,000, blah, blah, whatever the, the integer maximum, well, unsigned integer maximum is. So, so that's that. So, like I said, this is why you kind of have to know how it works, because you're doing this spinning and whatever, and you have to know what that means before you can really sit and tune those things. Now, InnoDB thread concurrency, if you do have a lot of threads, I'm just calling threads processes threads, even though they're different, but in MySQL they're kind of sort of the same thing. They're not really, but I'm just going to call them, I'm going to try to call them threads, because that's what they are. If you have a large number of threads that have been waiting for semaphores, it could be that you have some kind of, you have some resource contention. Either it's a lot of disk I/O, or there's some InnoDB contention problems. And one of the reasons you might have contention is if you have a lot of queries running in parallel. Think of like if you have, when we get the pizza here, right? We all run to the pizza. And it would be a whole lot better if, I could sit by my computer and continue to work while a few people get pizza, and then I can go and get pizza. And I can kind of make my time better like that, as opposed to everyone just going to pizza all at once. It's that same kind of, that's what InnoDB thread concurrency, will do. So if your InnoDB thread concurrency is set to 8, it means you can have 8 people waiting in line for the pizza. Basically, you can have 8 active threads in the InnoDB kernel at a time. That's completely different from, you can have 100,000 different queries running, but there will only be, let's say, maximum 8 if that's what you have as your value. That's the default value.
So if, for example, 10 threads compete for particular resource, but you put 8 only, what happens with the rest two threads? Are they going to die or whatever?
Well, we'll talk about that in a second. They're not going to die. What they're going to do is so the first 8 that go are going to get, places in line.
The queue,
well, they're going to get to run.
Mm-hmm.
and they're going to start running. The other two actually will be delayed for 10,000 milliseconds, which is 0.1 of a second. So basically, in order to, once you start having this contention for those 8 spots, or for the concurrency spots, InnoDB will actually say, okay, everybody now has to wait, so that it won't, it won't get worse and worse and worse. That's the theory anyway. So, and we'll talk about that in a second, but basically you can change InnoDB thread concurrency. You might increase it to have more threads concurrent, but which is usually a good thing, but you might also get better performance if you reduce it, because you have fewer threads trying to grab those resources. There's less contention overall. So if you've ever looked at InnoDB thread concurrency in the manual and it said, oh, start at like 2 times number of CPUs plus number of disks, or whatever their wacky formula is, and then if that doesn't work for you, change it up or down, and you're like, well, when do I change it up, when do I change it down? Well, would more concurrency be better or less concurrency? If you have a lot of contention, then it's better to have less concurrency, because things will actually go through, there'd be probably better throughput because things don't have to wait for locking.
How long is the delay there? You said 10,000?
10,000 milliseconds, which is 0.1 of a second.
No, it's 10 seconds. 10,000 milliseconds.
Yeah, I thought
Maybe it's
I thought it'd be
microseconds?
100
Microseconds.
Microseconds, okay.
0.01.
Yes, it is microseconds, not milliseconds. I'm sorry.
Um,
Yes.
What metric measures wait time? How long you're waiting if you have a lot of concurrency?
Oh, you mean like when we had all these shared spins and OS waits, how long did we wait? I don't think that we have that. I haven't seen that as far as I know.
If you had that, then you'd know whether you had too much concurrency or not.
Right. You do have, and I'll show you actually in some semaphore examples, you do actually have how long it's waited at each particular point for the semaphore. So for example, and this may be what you're asking. So this, in the semaphore section, you'll start with this, and then you might get to these things. So this is a thread number, blah, 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 and this is the thread ID that you see when show process list has waited at this line, this thing in the source code at this line for 242 seconds, and the semaphore is an S-lock on the read-write latch at whatever this hex value is, created in file dict, dicto, dict0, dict, line 1356, a writer, this thread ID, so see it's different for this thread ID. So this thread ID is actually reserved in exclusive mode. Number of readers 0, waiters flag 1, meaning that this thread is actually writing. And this thread either wants to read or write. We don't really know what it does, but if we went and read the source code and went to this file and went to this line, we would see where it is. Now I've actually happened to, if you actually go, I've put a URL here, forge.mysql.com/wiki/mysql internal files InnoDB sources, and then search in the page for that. I don't know, I don't think it's, there's only one page, so who knows, depending on what version you're using, it might not be completely accurate, I don't know. But the ones that I looked up were, were all there and looked good. So when I looked that up here, I don't know if you guys can see this, this is actually B-tree persistent cursor is what the page showed me. So it means that it's probably doing something with indexing or rewriting the B-tree if it's, if the data itself. So the data and indexes are usually stored in B-trees.
You get this from a WAF file or from show engine InnoDB status?
Did I get this
Or
part?
output?
You mean this part down here?
No, the top 3.
The top 3 is in show engine InnoDB output. But it's only if you have semaphores. So you might only get this information. Like if you're doing it on your machine and you don't see this kind of thread stuff, it's because you don't have any semaphores. Like this is just at the time, and I've taken all these examples from different places. So at the time, there was this semaphore. For all I know, it might have actually been, well, it wouldn't have been a spin wait, because after 242 seconds, it's an OS wait at that point. Here's another example, thread 8113, obviously different servers here. The threads are completely different. Has waited here for 1 second at ibuff 0 ibuff. So probably InnoDB buffer. That's what I'm thinking, some kind of buffer, right? You know, number of readers 0, reader select 0. Last time read locked in file. Here, last time write locked in file, that line. So this is actually the insert buffer. It's not InnoDB buffer, it's insert buffer. So this means that something is waiting for an insert on a table, or the insert buffer rather. But it means that you're probably doing a lot of inserts, you know, stuffing data in there. So again, you need to like know where to find this information, and you know, and again, I'm just kind of like guessing. It says insert buffer, but I didn't actually go to the source code to read that line of code. You can, and figure out exactly what it's doing at that moment in time that it's waiting for it. We also have this one, which actually came from the same server as this one, waited at srv.c, which is just the server. It's the server main program. That's it. I don't know what it was doing. You know, it was waiting for 0 seconds for this mutex, blah, 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 blah. So actually, and I have in my notes that the srv0 srv.c was actually caused by waits that they saw when a different query was doing select for update. So usually it's enough to get the general idea of like, oh, what is it waiting for? And I mean, it can be really, you know, it can be really useful when you're like, okay, there's a lot of InnoDB contention, but what is it? So does that help?
Yes.
Yeah. So obviously something that's waiting for 242 seconds for that, and for, you know, dict 0 dict, you know, I've also seen lock 0 lock, you know, this transaction, row 0 version, all that kind of stuff. So I can actually show you the page. So this is its internal files in InnoDB sources. So if I want to look at like dict 0 dict, it's the data dictionary system. So maybe there was an alter table going on, 242 seconds. So it couldn't even get to the definition of the table. That, you know, so it obviously couldn't insert into the table or whatever it was trying to do, update or read from the table. I've also seen lock 0 lock, which says the transaction lock system. Well, that, again, not very helpful, but you know, it's something that's inside of a transaction. So that might be enough information to kind of spark, okay, here's what it's doing. And you do have the thread ID. So if you do have a show process listing with that thread ID, you can cross-reference it. What else do I have? TRX 0 TRX. This is just the transaction, and so this is the general transaction one, which is what we had found, but I can tell you that it's not any of these. It's not in any of those. So it's not, you know, it wasn't locked in those files. So it was something about the transaction that wasn't purging old versions, wasn't undo log record, wasn't rollback, wasn't system, wasn't rollback send, wasn't undo logs. Again, you know, I haven't gone to the source code for these things, but there you go. And then there's row 0 vers.c. That's row version, and that's just row versions. So again, this is InnoDB uses MVCC, multivariable concurrency control. So it actually saves information about previous versions of data, because if you're doing, say, by default, MySQL uses repeatable read isolation level, which means that if you read data, even if it's already changed by some other process, you're going to read the same thing the next time you do it in the same transaction. So it needs to save that data somewhere.
Where does it save it?
It saves it inside the InnoDB kernel, and we'll actually, there's more to come about that on more slides. So so yeah, it's pretty exciting and pretty interesting stuff. I'm sure it'd be even more interesting if I actually read the source code, but. The next thing you have is the latest foreign key error, which if you ever get that dreaded error number 150, anyone got an error number 150 when they're trying to do a foreign key and you have no idea what you did wrong? I have. You know, you don't know, did I do the index wrong? Is the table I'm referring to non-InnoDB? Does the field not exist? You don't really get any hint. You just get error 150, I couldn't make the foreign key. Well, if you get that, you want to do show engine InnoDB status and look at the latest foreign key error. Now this was, I think this was actually taken from the same server that I did it at September 9th. Was it September 9th? Yeah. So this was actually the last foreign key error was August 18th, which is really pretty good, right? Last foreign key error was August 18th. It's now September 9th. And this was the transaction. It had been active for 0 seconds. Probably it was trying to create a foreign key or it was trying to insert a foreign key and figured out right away it couldn't do it. So it wasn't active for a very long time. Process number, here's an OS thread ID. So if you're using a debugger like GDB or sometimes LSOF or other system tools can give you the operating system thread ID. And it says updating or deleting. So it was trying to change data, either by updating data or deleting data. So it was only trying to use one table. So it used one table, locked one table. 4 locked structs is the number of, so it's a lock structure. So each lock structure could lock more than 1 or more rows. Heap size is the size in memory that the versions that I was just talking about, that's how much memory the versions take, is the heap size. And that's in bytes. So there's 2 row locks here. So it's, let's keep doing that. So there's only 2 rows locked, and there's 1 undo log entry. So probably what it had done is it had either updated or deleted 1 entry, and it was going to do the next entry, or it only deleted the 1 entry when it came upon this error. So here you see delete from DB table 1 where ID equals 1248083. So it actually locked 2 rows even though it was only deleting 1. Because what InnoDB will do is it'll try to guess, we'll try to guess at the range of locks it needs to get. So sometimes it locks a few more rows than it actually needs to, which is perfectly okay. So this is actually what it was doing. MySQL thread ID. So again, if you have the process list, you can find the thread ID, query ID. It was from the machine, Web02. Actually, it was from the user Web02 at the machine localhost. It was using the database test, and the status was updating. And updating status means any kind of data change, whether it's insert, update, or delete, just to make everybody confused. So it tried to basically delete this 1 record, and it couldn't. Why? Because the foreign key constraint failed for DB1 and table 1. The foreign key ID referenced table 2, T2 ID, so it actually couldn't delete. It couldn't delete or update, but we know it's deleted in the parent table in the primary key of ID because the child table still had a record. So this is not an on-cascade delete or anything. It's just it tried to delete it and it couldn't because there was another record there. So again, that's pretty helpful to know. And this is something that you want to look at because looking at this, I would say, wow, what did my application try to do a month ago that didn't work? And did I know about it? Does my application tell me, hey, this thing tried to delete something and it didn't work? If you do this and your last foreign key error was 5 minutes ago, you really want to look at it to see what it's doing. So basically, there's the 2 times that you can have a foreign key error is when you're updating, deleting, or inserting data because it's going to check those foreign keys, or when you're doing an alter table or adding a foreign key or removing a foreign key or changing a foreign key that already exists. Those are the times that you'll get that. So if you get error, besides error 150, I think it's error 1025 is when you're trying to rename a table. The reason that you get that error is because MySQL, when it alters a table, it actually makes a new table and then renames it. So that's that. Latest detected deadlock is the section that comes after that. Now you may not have this in your output if you didn't have a deadlock since the server started. If you did, now this is a lot to digest, so I'm going to look at the bold parts mostly because everything else is kind of pretty, it's either, I don't want to say it's obvious, but it's just kind of like, okay, that's informational, right? So here's the transaction you know, kind of, it's the sequence of the transaction. You know, it's been active for 0 seconds, process number, OS, thread ID, starting index read. That's useful to know. So it was starting an index read when this deadlock happened. Again, MySQL tables in use 1, locked 1. In general, actually, the latest detected deadlock is only going to show the last 2 transactions that were involved. So if you have like a 3-way deadlock, it's only like with 3 different, you know, transaction A has a lock on table 2 and transaction B has a lock on table 1, and then A and B want to use the other's thing. That's a 2-way deadlock. You can also have a 3-way deadlock or more. The show engine INNODB status is only going to show you the last 2 transactions involved and the last 2 statements in each transaction, up to the last 2 statements that were involved. So this may not be the complete picture, but it's probably enough to get you started, at least on looking at your code to see where these deadlocks might be happening. So I wanted to say that before we got into to the crazy going through all this. So let's see, MySQL tables in use 1, locked 1, lock weight 4. So that means that it has no, it's lock 1, lock weight, and then it's 4 lock structs. So the lock weight just is kind of like the header for this. So lock weight, it could have like a colon, 4 lock structs. And again, it's probably, where do we see the 4 lock structs before? We saw them somewhere, didn't we? I remember explaining them before. It's here. Yeah, the 4 lock structs. So it's probably, I don't know, because that was back in August, so who knows. Heap size 1216. No, it probably is. It's the same heap size, right? Heap size 1216. 4 lock structs. So it's probably the last deadlock was probably a month ago too. It doesn't really, I forget if it tells you the time of the deadlock or not. I didn't write it down here, so it may not. But at any rate, I think this last detected deadlock was actually the last foreign key issue. And so basically what you had here is, or maybe not because we don't have a delete, but it may have been using the same table with the same row size. So that same 4 lock structs locked a heap size of 1216. Select star from table where table 1.id equals 4344 update. So here's the thread ID again, query ID, localhost, so machine, database, status. So the status is statistics. You might have seen in show process list, you see a statistics status. So this was the query that was running, and it was waiting for a lock to be granted. Well, what was it waiting for? It was waiting for index primary of table test table 1, because it's, so if the index was being written to at this point, whether it's an alter table or an insert or an update was writing to the index at the time, it wanted to look up in the primary key index this value, and it couldn't because it was locked. So it was waiting to be able to grant that lock. And this is the transaction ID that it's, you know, waiting for the grant, all that kind of stuff. So that was, you know, I said it was, you're going to see the last 2 statements in each transaction. So this is transaction 1, and these are you know, the 2 statements there. This transaction is transaction 2, right? So this transaction, okay, we have an ID, active 0 seconds, okay, process number, OS thread ID, starting index read, okay, so that's the same as up here, starting index read. Thread declared inside INNODB 500. I'm going to go over that later, but that's important, and that actually, we're going to talk about that. When we talk about that, that has to deal with the delay that I was talking about before. So update table 2 set foo equals bar where ID equals 2891733. Okay, so this is the query that's locking table 1's primary key. Well, that's kind of weird. Okay, wonder why it's doing that. Well, 2 holds the lock, or the locks that 1 needs. So where's the lock? Index primary of table test table 1. Okay, that makes sense, right? Because it was trying to read that, and something has an exclusive lock on it, and so I can't read it. But why would it have that? Well, let's see. It's also waiting for this lock to be granted. Index primary of table test table 2. Huh, so this is probably this deadlock situation where transaction 1 is waiting for table 2 lock, and transaction 2 is waiting for table 1 lock, but the other transactions have that lock. So what do? You roll something back. So in this case, MySQL rolled back transaction number 2, or InnoDB I should say, roll back transaction number 2. InnoDB will actually roll back the transaction which has the fewest updates done. And I believe in the case where, like in this case, it hasn't done any updates, right? Because it didn't do this update because it hadn't finished. And it didn't do this select. It's going to do, I don't know how it decides which one it does, if the amount of data updated was the same. Maybe it could be the first one. I would prefer that it rolls back the read as opposed to the write, but you don't know what's inside of a certain transaction. So now we're going to talk a little bit more about transactions in general. The transaction ID counter. This is just the transaction ID. We've seen it in other places. Transaction 0213380 whatever. There are 243. So this is the same. This is the same server, pretty much, that I've had the whole time. Purge done for transactions, and then undo. So the purge is actually, this is the multivariable concurrency control, MVCC. This is purging those old versions. Okay, so this is the transaction ID that we're on now. Okay, we've actually purged up to less than this transaction. And in the undo log, there's no transactions. So basically, if there was a number here, it would show which transaction has the latest version being purged. So that would be in the undo log, basically, if we had that. So this you can see, okay, 243137723, 243137700. So this has, 23, transaction IDs more than this. So that's actually pretty good. The history list length is 25. The history is actually the number of unpurged transactions in the undo area. So, okay. This undo is actually the if there was a purge happening as I did show engine InnoDB status, that would be the number there. So it would be saying, I am purging this right now. So there is stuff in the undo log here. There's 25 IDs. So here the difference is only 23, but there's 25 there because it's always going to, if it's going to default to keep, it's going to keep a little more than it's actually purchased. It's not going to always be exactly 100% precise because that would take too much overhead. So it kind of does the approximation and errs on the side of keeping too much.
So all those threads essentially happened because MVCC.
Yes. All those threads happen
because they really talking about the same item which was updated and deleted or something. That's why they have to keep that log and compete for that particular item.
Well, there's not competition because MVC, there's
right,
not
compete, but
right.
dealing
Yes,
with
you have to
that.
deal with the overhead of keeping all the
Right.
different versions of information. So when you type start transaction, if you're doing a transaction, you type start transaction, InnoDB is gonna whenever you look at it, tables and stuff, it's gonna memorize. Okay, you looked at this table in this row. I'm gonna save that data somewhere just in case some other transaction comes along and changes it by the time you're done with the transaction. So you want to make sure that you don't have a lot of uncommitted transactions that are just waiting and sitting around doing nothing, because that's going to use a lot of resources. It's going to use memory to save those versions. Yeah, and threads and a little bit of CPU because each thread does a little bit. But so you certainly don't want to have those extra versions lying around. If there's a huge difference here, and we're going to have another example, I think next slide. Yeah. of something that looks a lot different. So here you'll actually see, this is actually where sometimes you get really long output because it just lists the transactions. So you'll see a lot of these transaction not started. These are your, doesn't have the concurrency yet. So if you have InnoDB thread concurrency set to 10, you're only going to have 10 of these transactions that are in the state that's active or something. You're going to have everything else. If you have 100 threads, they're all going to be in not started, or they're going to be in waiting or something. But a lot of them are just not started. Again, process number, whatever, MySQL thread ID, query ID. Here's the user. Here's the machine. This is different from before when we had the username and then the machine. Standards are great. That's why we have so many of them. I don't know why they did it differently in this section rather than that section. It's probably just how the data is saved internally in InnoDB, so it's just easier to just kind of flash the information there. So this process here is actually doing the show engine InnoDB status. This transaction not started, OS thread ID. I don't know what this one's doing. It's probably sleeping because there's no actual query there. This query this is the status, has read all relay log waiting for the slave IO thread to update it. That's the status. There's no query. Who knows what this is actually doing?
What's the
Verification.
What is it doing at that point?
What do you mean, what is it doing?
Yeah, well, I mean, at what state? It's not started.
This is actually the status. The status is has read all relay log, waiting for the slave IO thread to update it. And if you do a show process list, that's the status that you're going to see for replication. So that's actually, if you're on a slave and you do show process list, there's actually two processes. One is the IO process, which will go and read the relay logs for the master, and the other is the SQL process, the SQL thread, which will apply from the relay logs that it's read from the master, will apply the SQL statement. So this is actually the IO thread from a slave. So this machine that this was done was a slave. And again, this thread is there but not really running. So actually, let me go back here because I didn't actually when we're talking about purges, purge done for transaction number, if you have a lot of inserts and updates, your purging is going to be way far behind. Okay, so this is only like 23 transaction IDs behind. If you have something like 3,000 transaction IDs behind, that's bad. That means that you can't really keep up to date with all of your inserts and updates that you're doing. So what you can do is you can actually set a purge lag, and what you end up doing is you end up you basically delay data change statements like insert, update, delete. You delay DML so that the purge actually has time to run. And that setting is called InnoDB max purge lag.
The purging is done by separate thread of control. It's not done sort of in the process of the update. If I do an
Correct.
update, I'll then.
And there, because otherwise you would always be waiting to either flush the data or sync the data, and that's usually not desired. So it says when purge operations are lagging, this controls how to delay insert, update, and delete operations. Unfortunately, it's not just like, oh, delay all of them or delay by this much or whatever. This is actually, let's see, the transaction system maintains a list of transactions that have delete marked index records. So if you basically have deleted some data, if you do an update, what it will really do is it deletes that little, column in that row and then inserts a column in a row. That's what it's doing under the hood. It's different from replace, which actually will delete a row and insert it again. That's just when it says delete marked index records. That's just if you're doing an update and you change, something that's an index. If you're doing a delete, it has a list of the transactions that have actually done that. So basically, when the number of those transactions that have that delete flag on it exceeds the value of purge lag, if it's set higher than 0, then it delays it by some calculation of whatever that it does internally, based on the number of transactions divided by ENODB max purge lag, times by 10 minus 5 milliseconds. Computing the beginning of a purge batch every 10 seconds, blah, blah, blah. I have never set this. Usually, if you're doing so many inserts and updates that you can't keep up with purging, you want to figure out a different way to do what you're trying to do. Maybe use like insert delayed or some kind of other mechanism, because setting the delay for the purge lag is only kind of buying you a little time. It's not really solving the problem. It's just, I mean, I guess it would be good if you have like very bursty behavior, and so you want to kind of just spread that load out for a little bit. But
hoping that in the next 5 seconds you're not going to have anything like that.
right, and that's why it's specifically if you know that you have bursty behavior, that you get a short burst and then nothing, and then a short burst and then nothing.
For the web traffic, it might be reasonable.
Right, but most people just have continuous web traffic, right, and that ramps up and ramps down. But you know, it's hard to say, you know, on what scale the burstiness is, right? Is it milliseconds? Is it microseconds? What's that scale? So hard to say. So they say a typical setting for problematic workload might be 1 million, assuming the transactions are very small, only 100 bytes in size. I mean, 100 byte transaction is very small, and is allowable to have 100 megabytes of unpurged ENODB table rows. So again, it's only when you exceed that 1 million number that it starts putting that delay in there. So we've seen this. So we've seen some stuff like this here. Here, active 292 seconds. So active 292 seconds. Process number, OS thread ID, starting index read, thread declared inside ENODB 15. Now I showed you something that said thread declared inside ENODB 500 before, and said we're going to get to that later. Well, we're here now. So what this means is the thread is inside the ENODB kernel. It's not in spinning, it's not in OS wait, it's actually in the kernel, it's running. Okay? It only has 15 tickets left. What's a ticket? A ticket is every query gets 500 tickets to start, and every time it goes into the ENODB kernel, it uses 1 ticket. When it runs out of tickets, it goes back into spin wait and then OS wait if it has to do that. So this kind of gives it gives all the queries like a little priority of like, okay, you can start, and you get a certain amount of processing you can do until I put you to the side, because I'm trying to do lots of concurrency here. I'm trying to get everyone through everything I need to. Now, if something's holding a lock and it gets put aside, it still has that lock. So it doesn't really help with locking issues, but it does help with, so that there isn't one long query that MySQL is just going to spend all its CPU and all its memory on one query. So here, this one's almost out of tickets, which is good because it's been active for 292 seconds. That's kind of a long time. It's almost 10 minutes, right? 300 seconds is 10 minutes, 5 minutes? 5 minutes. It's almost been going for 5 minutes, so. MySQL tables in use 2 locked 0 holds adaptive latch. We're going to talk about the adaptive, it holds an adaptive hash latch. We're going to talk about the adaptive hash in a little bit in more detail. But basically what it is that ENODB tries to be smart, and it tries to make adaptive indexes that will be much better for you to use than the indexes that are already there. And so holds adaptive hash latch means that it's doing something with that adaptive hash. Maybe it's deleting it, maybe it's rewriting it, it's doing something. It's been doing something for 292 seconds. So this is probably an alter table or a very big insert or update or delete. So the fact that it's probably changing data or table structure, which also changes the data, which means it's changing the adaptive hash. That makes sense. So again here, this is transaction 1. Copying to temp table, again, something else that we think probably, if it's copying to temp table, it's doing some big query. Alter table will usually copy to temp table. It could be an alter table, it could be not. Oh, and in fact it's not. It's select table 1 from table 2, left join, blah, 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 order by these two things. So, so it's actually not even an alter table, it's just, it has a read lock. And it's just been going for a long time. Probably these tables have a lot of IDs in them, or maybe there's no index. Probably is an index because the fields are called ID. So this transaction read view will not see transactions with ID greater than that. It sees IDs less than this, 436. And it won't see anything with ID greater than 457. So there's your multivariable concurrency control right there. Which means that when it's purging, right, it's not going to purge 9437436 until this query is done.
Is it from explain statement you can find that numbers less or
The transaction ID? No.
no, ID more than will not see transactions with ID this and that. Is it from where?
No, that's just from the internal transaction ID, like this here, transaction 944056. So this is transaction 456, so it's not going to see anything greater than or equal to 457. And it sees less than 9437436. I wonder if that's, no, 9437436. I have no idea what, because you would think it would say sees less than or equal to 944 or 456. But basically, that's your multivariable concurrency control. This is what I'm seeing. I'm not going to see that. I'm seeing this. This could be the number of transactions that are happening at the same time, that they all kind of opened up at the same time. So it's not going to see the changes from transactions that are current. Also, it's only going to see from before it started. So we talked about InnoDB thread concurrency. I already mentioned InnoDB's thread sleep delay. That's the that if there's no free slot through InnoDB concurrency, InnoDB will make a thread sleep for a really small amount of time before entering the kernel, which is these are all status variables that you can change. So this is the status variable InnoDB thread sleep delay, and in fact I say value is in microseconds, 10,000 by default, or 0.1 seconds. Let's see. My other notes say that, this MySQL tables in use 2 locked 0. So it does actually have a read, well, it doesn't have a read lock because it's InnoDB. The lock is actually a table level lock. So you might even see a write that has 0 locks on it because it's not a table level lock. The only way you're going to see a table level lock on an InnoDB table is if you've specifically done a lock in the table or you're doing an alter table. So InnoDB commit concurrency is how many simultaneous commits you can have. Now obviously it depends on InnoDB thread concurrency, right? You can't really have more commits than you have threads running at a time. 0 means unlimited. So basically you're not really limiting how many threads can commit at one time. You're just depending on InnoDB thread concurrency to limit the number of concurrent threads, period, in the InnoDB kernel.
Why do they want to limit the number of commits?
I have no idea. The question is, why would you want to limit the number of commits, especially if you're already limiting the thread concurrency? I don't know, maybe if you have contention, like if two things are...
I/O reduction?
Yeah, I/O reduction maybe. I have no idea. I've actually never set this differently. But the default is 0 and it's unlimited. The default for InnoDB thread concurrency is 8. So I think they kind of want, they kind of say the best way to deal with the concurrency is to use thread concurrency unless you really, really just need the commit concurrency. And then InnoDB concurrency tickets, we talked about, the default is 500. So if you're finding that your query load is such that you want to be able to kind of have more throughput, so if you have tons of small queries, you might actually want to reduce the number of tickets. Because then your small queries will go through, your larger queries will more quickly get to the point where they have to wait. I've never actually changed the commit tickets either because, again, it's very difficult. You're changing the behavior for every single query on an InnoDB table. I mean, you're changing it for every single transaction. And that's a heavy thing. You know, you might want to say, well, let me just change it for this one, you know, this one set of queries or something. You can't really do that. So that's all I have for that. It's going to get less heavy from here on in, I think. So this is really kind of heavy internal stuff, but it's good. I think it's good to know, especially because you probably, I know, I can't tell you how many hundreds of times I look at, you know, show engine INNODB status, and I just see all this data, and I'm like, let me try to pick out what I think makes sense to me. So file I/O. So I mean, I think it's neat because you can also, you know, a lot of times you'll go through like, well, how do you tune this number and how do you tune that parameter? And this is actually how you find those INNODB variables to tune, is you look at show engine INNODB status. File I/O. So on Unix, the MySQL manual says on Unix there's exactly 4 of these. On Windows, there's actually an INNODB file I/O thread system variable, which you can change, but that's only on Windows. On Unix, they say it's always 4. When I looked at show engine INNODB status on a Percona build, there were 17 different ones, not 4. So they just had tons more. They had the same one insert buffer thread, one log thread, but they had tons more read and write threads. So I'm going to guess that that's how they get the higher performance, the higher concurrency, is by having more read threads and more write threads.
They said that for old hardware, INNODB assumed that only one thread or a couple of threads doing writing and reading, and they claim that now we increase the number of threads which work with the buffer simultaneously. That's how we increase performance. That's how you probably see why you see more threads
Yep.
than official MySQL documentation claims.
Yep. So, yeah, I have proof that Percona is actually doing more reads and writes because they have more read and write
Could you
threads.
say what Percona is? Because I apologize, I don't know what that is.
Sure. Percona is actually a consulting company for MySQL. It was founded by former engineers at MySQL. And they actually have a patched version of MySQL they offer for free. So there's an insert buffer, log thread, a read thread, and a write thread. If any of those are waiting, not waiting, if any of those are specifically not waiting because there's contention, right here it's waiting. It's basically saying I'm waiting for INNODB to give me a request. I'm the log buffer, I'm the buffer thread, and I'm waiting for INNODB to give me an I/O request because I don't have one. Okay, if it's not waiting for an I/O request, if the state is, I don't think I've really ever seen it in any other state other than waiting, but I don't have an example here of a state other than waiting, but you know, that's where you have your contention. So if you have it in the insert buffer, you might want to see if you can make those buffers bigger because you have contention in that buffer, or it means you're doing too many data changes because the insert buffer is being used so much that there's contention for it. Log thread, same thing. Maybe it's making your log file size bigger. Maybe it's making more log files in the group. You know, maybe it's the fact that you have so much that you're doing with writes that it, you know, has to log all those writes. Read that write thread again. If you have lots of, you know, reads, you know, in contention with each other, you know, maybe if these write threads, if there's a lot of contention there and you see it here, that might be a reason to do the commits, to change the INNODB commit concurrency differently. So the insert buffer thread does insert buffer mergers, which is basically when you change data in INNODB, you change the data in the buffer pool, and then pages in the buffer pool will be flushed to disk, so changed on disk. So what it can do is it can batch together, MySQL calls it merging, but it will batch changes that are on the same page if they happen close enough to each other, you know, in time. So that you might have 6 rows changed, but it's only doing 1 write, and that really helps. That really helps improve performance. So the log thread does log flushes, which are asynchronous. The read thread does read aheads to prefetch the data that INNODB thinks it might need, and the write thread is what flushes the dirty buffers. So. Everything else here, pending normal, AIO reads, AIO writes. iBuff is the insert buffer, AIO reads, syncs. the log IOs and the sync IOs, pending flushes. So again, it's basically just taking the status and then seeing, okay, here's the status and then here's the pending ones. And obviously if the status is waiting, all of the pending stuff should be 0. There's nothing pending if it's just sitting there waiting. But if you have a backlog, if things aren't just sitting there waiting, if they're in the middle of like, okay, I'm doing this right now, you can see how big of a problem it is by seeing how many pending, reads, writes, syncs and insert buffers are going on. So here you have, number of file reads, number of file writes, number of f-syncs. So here you only have like 800,000 f-syncs, but those 800,000 f-syncs wrote about double the amount, 1.7 million file writes. So an f-sync can write more than one file. So this is reads per second, average bytes read, writes per second. There's 2.28 f-syncs per second, which, is a lot. I've seen, that just means that you're doing a lot. There's a lot of data being changed. In fact, one thing that I've seen is I've seen people using InnoDB tables for things like logging tables, where you're really just doing a lot of inserting and maybe some reading, but not really any deleting or updating, but mostly inserting. Very, I've seen this on servers that are, 88% reads, 88% writes and like 12% reads. So it's really just inserting in log tables. And they had them InnoDB, and they were having a problem because their inserts would back up.
Better to use ISAM.
Yes, exactly. Better to use my ISAM with the concurrent insert flag set, which it sets default to 1, than it is to use InnoDB, because InnoDB has this double write buffer, right? It writes to the buffer and then writes to the disk. That's two different things that it has to do. With my ISAM, it just writes to the disk. But sometimes it's hard to, because you start out, they probably started out with my ISAM in it, and then the concurrency was too much, and so then they went to InnoDB, but then, they couldn't quite do everything.
What's the time frame for those averages?
What's the time frame for the averages? The last 12 seconds? Remember we were talking about way in the beginning, the header?
Yeah, it's the same.
Yep, it's per second average is calculated from the last 12 seconds. So that's what these per second, reads per second, bytes read, writes per second, f-syncs per second. There are status variables from InnoDB. If you do show global status, you'll see that there are InnoDB, writes, how many times it called, InnoDB writes, things like that. So you can get a longer average, which is basically since the last time you flushed, or since the last time it's uptime, like last time you did flush status, or last time the server restarted, if you want a longer average there. So the adaptive hash index and the insert buffer, but mostly this is the interesting stuff to me is the adaptive hash index. So let's just get the insert buffer out of the way, I guess. So basically, the insert buffer is when you're inserting into InnoDB indexes that are not unique and not the primary one, obviously. So non-unique secondary indexes, InnoDB might put records into the insert buffer and then flush in their disk after the transaction commits. So it actually waits until after the transaction commits to actually flush to disk, to do that disk call. You can't do that with unique keys or primary keys because with a unique, primary key is a unique key, but if you do that with a unique key and you delay that, then somebody else might put the same unique key in there, and then you would have a problem because you can't have duplicate keys. So it's only for the non-unique indexes. So again, that's why it's not really as interesting to me as other things. So hash indexes are in-memory indexes. So here you've got, however many inserts you did. They did 36,000 inserts, 36,924 merged records, 27,000 merges. Now, the hash index, I don't know, I'm not really, so basically the ratio of how many merges versus how many inserts is how efficient the insert buffer is. So here it's not very efficient, right? Because you've got 27,000 merges versus 36,000 inserts, right? So you could say that about maybe 2/3 of the inserts are not being merged. There's only about 1/3 being merged. Now, is that good or bad? I mean, it's better than nothing, but it's not as good as having, say, 50% of them merged. And again, it's really hard to change these values. It's not like you could say, oh, make my insert buffer bigger. There isn't really a status variable like that. So you could try to reduce contention, things like that.
So the rest of the inserts which has not been merged, inserted into the files one by one, but the 2/3 were aggregated.
Well, 1/3 were, yeah, 2/3 were aggregated.
Or aggregated and one.
And 1/3 was not, because it just couldn't be. So hash tables are memory tables. Hash is just memory. And basically, let's see, there's a mechanism in InnoDB that will monitor index searches that are made to already defined indexes. And if it notices that the queries that are doing that could benefit from building a new index, like from building a hash index of those, it will do that. So indexes are B-tree indexes. And so what it will do is it will automatically, again, adaptive hash. On an adaptive basis, it'll make these tables. So it will
sorry, is that in memory or is that on disk?
It is in memory. Hash is memory. And it's not anything that you can't really say flush the adaptive hash, like get rid of the adaptive hash for this table. InnoDB, it will build on demand for index pages that are accessed a lot. So it's not necessarily going to build a hash for the whole index. Just if InnoDB notices that it's always accessing certain pages of data, it'll actually create a hash index for that one. So you have the.
So what are you saving? What is saved as a result of that? Is it avoiding the higher level B-tree page lookups before you get to the actual page of data, or is it?
Exactly. It's just doing the hash lookup.
I don't get that. I mean, you'd figure that those B-tree index pages are going to be in memory anyway if they're being hit a lot.
Apparently, it makes things faster. I don't know why, but apparently the adaptive hash searching is just faster and better, theoretically. There have been times where it's been buggy and things like that. So the ratio of hash lookups to non-hash lookups shows how efficient the adaptive hash index is. Now, I don't know if that shows how efficient it is. That's what the manual says. It actually shows how many times it's used. Whether or not, so this is being used 2 hash searches per second, 17 non-hashes, non-hash
How
searches
often it's
per
used, but
second.
not how effective it is.
Right, it just shows how often it's used. Now, who knows? It might not be used very often, but be very efficient, so that you're saving a lot when you are using it. We have an extreme example here, where here's 8,457.31 searches per second and 17,000 non-hash searches per second. Yeah, these are real numbers from a real server. It's pretty crazy. In here, so InnoDB buffer pool pages MISC. This is actually the place where the data pages, or the pages that are used in the buffer pool to store these adaptive hash indexes. So there is the overhead of the memory, and that is used in these InnoDB buffer pool pages MISC. On this particular server, it was over a gig. It was 11% of a 12 gigabyte InnoDB buffer pool.
Is it that, or is it reporting this is how much we've decided to use?
No, we don't get the choice. We don't.
But that's the thing. So it's reporting. It's not saying.
It's a it's a status variable. It's just showing you what is currently being
What would
used.
have caused that situation, Sheeri? Any theories?
I mean, it made a lot of index hashes. It decided that there were so many. I mean, it's a 12 gigabyte buffer pool, right? So you have a lot of. Obviously, there's a lot of data. There's a lot of data being accessed frequently. So InnoDB automatically made the adaptive hashes. Now, one of the things that we actually recommended for this client was to test turning off the InnoDB adaptive hash to see if it works. Because just because it's using it, 7-8 times more than not using it doesn't mean the overhead is worth it. And that's a lot of overhead. That's another gig of data. Now, granted, this client had, 80, 100 gigabytes of data, so it's not like that 1 gigabyte in the buffer pool is going to make a difference. But, sometimes you just need to play and see, like, well, what does it look like without the buffer pool? What does it look like without the adaptive hash? What does that look like?
Does
So-
turning it off help?
Yeah, did they do that?
Well, they didn't, no.
They didn't?
They didn't, they haven't tried yet.
Ah,
So this was a
interesting.
recent recommendation. And I actually updated this slide, like I did this at the beginning of last week.
But is it possible to influence how many searches you have to have in order to turn on that feature?
Nope.
No,
There's
just,
no-
just
yeah.
they decided.
You can turn it on and you can turn it off.
Turn it off,
and that's
yeah.
it. And in fact, the only reason you can turn it on and off is because there was a bug in the InnoDB. Yeah, there was a bug in it that made it worse. The bug was actually fixed in MySQL 5.0.54, but before it was fixed, they made a flag in 5.0.52. They made the flag to turn it off, and they actually fixed it in 5.0.54. So you should actually be careful if you're running anything less than 5.0.54, because if you're using, say, 5.0.45, which is, I think, Red Hat Enterprise Linux's currently supported version that if you do, yum update or whatever, that's what you get. This adaptive hash could be buggy. Now, this particular client was not, they were using 5.0.54a on one machine and like 5.0.85 on another or something, so they weren't, this wasn't a problem for them. Just because the adaptive hash is being used and just because it's a lot doesn't mean that it's necessarily good. But it doesn't necessarily mean it's bad either. So this is one of those things that, and that's also hard when we're recommending, clients don't want to hear like, well, we suggest you play with it and see. They want us to know what's going to happen. We don't know what's going to happen. There's 8,000 of these searches per second. For all we know, it's a total waste of overhead, and for all we know, it's the best thing to happen to this server is to have the InnoDB hash, because it's 8,000 searches per second, it's using it.
But it is still very important. So you tell version 5.4, it works, it is not buggy, and it could increase your performance significantly.
Right.
That's nice.
But it's on by default. The InnoDB adaptive hash is on by default.
If you use 5.4
No, 5.0.
or 5.0.45,
Right.
yeah.
It's been in
Right.
InnoDB. The InnoDB
Right,
adaptive hash
right.
has always been in InnoDB.
Mhm.
It's just
Right.
starting in 5.0.52, you can turn it off.
Ah, okay.
Because they found the bug, they didn't have the time to fix the bug, or they didn't locate it.
Okay.
They fixed it in 5.0.54, but in 52, the version before that, they wanted to give people who were suffering some kind of way to not suffer. So they didn't take it out once they fixed the bug, which is probably a good thing because it's good to have the option. But in general, you probably want it. Log. So these values are mostly numbers in bytes that represent the log sequence numbers. This is for the InnoDB, the log buffer, and the fact that it does the double writing, or it writes. So when you make a change, it'll write the change to the log, and then it writes the change to the data page, such that you always get the ACID compliance. You get the integrity, the durability. If you made a change and the database crashes before the data page is written, it's still in the undo. It's still in the redo log. That it can just redo that if it crashes by that time. So basically, this is where we are in the log sequence 1A12523962. We flushed the log up to here 129, so this is in bytes. So there's 800 bytes that haven't been flushed here. So that's pretty good. So basically, if for some reason, and this is log flush to disk. So if we have to shut down MySQL right now, the overhead of shutting down is going to be this 800 bytes to flush it. Sometimes it can take a long time to shut down if you flush the logs. If you have to flush the logs to disk and there's 17 megs of logs to flush, it can take a long time to flush that. This server particularly doesn't have that problem. And the last checkpoint was at 506173. So the last checkpoint was actually, 16 and a half kilobytes ago. I did the math. The unflushed data is about 0.8 of a kilobyte. The last checkpoint where a checkpoint marks a certain state when the data in the log file were in a known state and can actually be used for recovery. So again, 16 kilobytes, not that big of a deal. You know, obviously you don't want to lose anything. But the last check, you still have the logs. The last checkpoint. So if you had to recover from, if InnoDB crashed right now, you would lose, 8 kilobytes of data. 0.8. You'd lose 800 bytes, which probably is mostly header information or something. I mean, you probably would just lose the current transaction. The last checkpoint was 16.5 kilobytes ago, so the crash recovery would have to recover those 16 kilobytes from the logs. Not a big deal at all. So if there's a lot of unflushed data, so we had not even a kilobyte of unflushed data, but if you have a lot of unflushed data, you might want to increase the InnoDB log buffer size, because that's the size of memory that it does before it flushes to disk. So if you increase the amount of memory, it'd be less of a percentage. There'll still be the same amount of data that's not flushed, but less of a percentage, because you don't want the log buffer to fill up and then have your data change statements waiting on the log buffer to flush to disk before they can commit.
It's a performance issue, not the safety.
Right. It's a well, but it doesn't change the safety at all.
Yeah.
If you make the log buffer bigger, it doesn't change the safety, but you have less of a risk of having to wait until the log buffer, flushes to then do a next write. And now again, you can see here was one pending log write. Sure, because this log hasn't been flushed, so there's one kind of in the queue. I can believe that. 0 pending checkpoint writes. Okay, so it's not doing a checkpoint anytime soon. But that's in the next second or two, probably not doing a checkpoint. I don't know how frequently it does these on these things, and it's doing. It did 742,000 log IOs since the thing started. It's doing 1.5 log IOs per second. So sure, it's doing two log IOs every 3 seconds. I'm not surprised there's one pending. Every 1.5 seconds there's one done. So that makes a lot of sense. So I'm going to show you another set of numbers. So here, not such a big deal. Here, you have the log sequence number is the exact same as the log flush number. Now this particular server actually had, so there's a parameter called InnoDB flush logs at transaction commit, which means that when you commit a transaction, the logs are flushed. Now there's
every time when you commit
right.
a transaction, every time the
right.
log is flashed, versus you can do that not every time, but
right.
aggregating
well,
something.
once per second. So
Right.
there's 3 values. The value of 1 is the default, which means yes, flush logs at transaction commit. And so what that does is at transaction commit, it will flush the InnoDB log buffer to memory. So it flushes the changes to memory, then it flushes the changes from memory to disk. It does both. A value of 0 flushes both once per second. Flushes to memory and then flushes to disk once per second. Now if you flush at transaction commit, if you set it to 1, and it flushes to the memory and the logs after each transaction commit, that's a durable change. That's ACID compliant. It's a durable change because once you've made a change, it's on disk. So even if you the change itself isn't necessarily on disk, but the fact that you wanted to make the change, that log buffer has been synced. So if you do crash and you do crash recovery, that disk, that log file on disk, has the fact that that change needs to be made. Okay, if you set it to 0, you're doing it once per second. So you lose that durability. Now it's consistent. Because you have you still have that 1 second, right? So it's not durable. It's not going to be ACID compliant because you're not durable. But you have the log file in memory is going to match the log on disk. So if MySQL crashed at that moment in time, you wouldn't lose anything from the disk, from the memory to the disk. You would lose something because it didn't get flushed in the memory, maybe up to 1 second. But anything that happens to be in the log buffer in memory is also on disk. And that's why in this case we have log sequence number is the same as the log flush, because as soon as the transaction commits, it's gonna flush it. Now, this particular setting was InnoDB log transaction commit equals 0. The other value you can have is 2, which is an overloaded thing. So it's 1 by default. The value of 2 means flush the InnoDB, flush the logs to the memory after each commit, but flush to disk once per second. So this reduces the number of disk IOs. If you're having a lot of file IO, it reduces the number of disk IOs. It's not durable because you have the information in memory, but if the server crashes, the memory's gone away. But at most, you're going to lose 1 second worth of data, which honestly, if you end up crashing, a second is, yes, somebody might have already done their online banking transaction in that 1 second, but for the most part, if you ordered something from Amazon.com and it didn't work, or your submit page didn't work, you'd be like, that's weird, submit page, oh, okay, it worked this time. It wouldn't be a big deal to lose that 1 second of data for some applications.
If it is not a financial transaction.
Right. Or if it's one such that, it'll roll back and...
Yeah.
And then the last checkpoint here was a long time ago, 419 instead of 420. Last checkpoint was actually over 17 megabytes ago, according to my calculations. So, but this is also a very heavy, write server. So it's actually, so this is interesting. It's actually got fewer IOs per second, but more IOs overall, right? No, not more IOs overall. Interesting. Well, that's the last however many seconds, so it's hard to say. But this particularly was from a very insert-heavy server. I think it was from that one that I was talking about, those 88% writes. So it may be still doing checkpoints at the same approximate time, but it's just 17 megabytes have been inserted by that time. All right, buffer pool and memory. The total memory allocated and the additional pool, the additional InnoDB buffer pool, are in bytes. These are variables that you can set. So this server is running like 2 gigs of memory, I think. And then like 2 megs in the InnoDB additional memory pool.
What's the difference between those pools?
The buffer pool is the
No, between total and additional.
so that's the InnoDB buffer pool is the amount of memory allocated. So blah, blah. If InnoDB runs out of memory in this pool, it starts to allocate memory for the operating system and writes warning messages to the MySQL error log. I don't think I've seen this message in the MySQL error log, and we actually like monitor and page if something gets put into the error log. That's that we haven't specifically ignored. So
Probably the size of that pool is not huge.
well, it's 1 megabyte by default. So so here they've actually changed it to 2 megs instead of 1048576. They've actually changed it to 2096. This is 2 megs instead of 1 meg. So they might have actually seen those warnings and put it in there. The dictionary. So here's the additional pool. Here's how much has been allocated, which is over a gig. So they were right in increasing it.
What OS are you running on this example?
This is CentOS 5.3. So this buffer pool size is actually in pages. So if you wanted to find out what the size of a page was, you divide this by this and you get the page size. Free buffer is 0 because it was all in use. Modified database pages, oh, how does it do that? Database pages 94074, so 94,000 pages are in the buffer pool. 565 of those are dirty. They've been modified. So that's 500 out of 94,000. That's a pretty low percentage of dirty pages. Pending reads 0, good. We like pending 0. Nothing's waiting. Pending writes, least recently used buffer 0. Flush list 0, single page 0. So single page is those writes that it can't merge. That's a single page write. And I honestly don't know if InnoDB gives like precedence in the writing to merged pages versus single pages. Maybe it does, I don't know. Again, I haven't really seen this, you know, anything that's really not pending. So total number of pages read, number of pages created, number of pages written.
All these numbers, are they since you enabled this monitoring?
Nope, since you started MySQL. Or probably since you started InnoDB if you have a plugin. But, yeah.
All right, so if I toggle this monitoring on and off, this just keeps going, all these numbers keep going up.
Yes, yes. And if you never turn on the monitoring and then either turn it on with the monitor or actually just type show engine InnoDB status, the counters, you know, you don't have to turn on the counters or whatever.
That's why they keep it. So if you want to look at that, they have enough statistics
Right.
to give it to you. Otherwise, they would.
Right, right, exactly. And some of them are kept in show global status with the, you know, if you do show global status and you see things that's like everything that starts with the InnoDB, you'll see, you know, you might see, I don't know if you see pages read and pages created, but you'll see like number of inserts, number of rows inserted, things like that. So some of either the same or similar information is actually in show status. I wish they could just put it all in show status so we could have one place to look instead of two places, but, you know, I want a pony, so.
More consistent terminology as well.
Yeah, 1 read per second, points and create per second, 0 writes per second. Buffer pool hit rate, 962 out of 1,000, that's pretty good, 96%. And of course, it depends. I mean, if this is the 12 gigabyte server, then sure, 96% is great. If it's a 1 gigabyte InnoDB buffer pool, not so great. So yeah, I think this is like a 2 gigabyte. 9265741, yeah, 1.8, right, K meg gigs. It's 1.8 gig, approximately, if you're doing it by thousands. The flush list that we see here, this flush list, 0, that actually holds the pages that have to be flushed by the checkpoint process. So I'm not sure if, I think that means like if a checkpoint is happening right now, it has the list, because obviously none of the servers that we've seen so far have actually been exactly the same with the checkpoint. Modified DB pages are pages not flushed to disk yet, which I said, but this is data, so don't confuse it with, we talked about log, flush logs at transaction commit. That's the buffer log, not the buffer pool. I got confused one day when I was seeing you know, data F syncs per second, and I'm like, how is it more than 1 when you have it set to, you know, every second flush the logs? And it's because it's logs, not data. So the last one is row operations. So 0 queries inside InnoDB, 0 queries in queue. This was taken from a server that wasn't, you know, there were 0 queries inside the InnoDB kernel, right? So if you had 8, if your InnoDB thread concurrency was 8 and you had 8, you know, you had 10 threads that were trying to use it, there would be 8 in the kernel, in the InnoDB kernel. There was 0 queries in the queue. There was 1 read view open inside InnoDB. The read view is a consistent snapshot, you know, the MVCC snapshot of the database at the point of the transaction started. So basically, there's 1 query that is kind of almost finished, right? Because it's not in InnoDB, and it's not a query in the queue. So it's probably this, show engine InnoDB status, because this is actually the very last thing that shows. Main thread, process number, whatever. Here we're flushing the log. Number of rows inserted, updated, deleted, read. This is not, this is just from the beginning. So this is the same, I think there's a status variable called like InnoDB rows inserted. So this is the same counter variable. This is just from the beginning, number read, and then you've got inserts, updates, deletes, and reads per second from the last 12 seconds. That's about it. We talked about a bunch of, we talked about what you see in show engine InnoDB status and how to tune at least these variables. We saw a few more in there. But thread concurrency, adaptive hash index, sync spin loops, thread sleep delay, commit concurrency, concurrency tickets. We had a few more like the purge lag one that I didn't put up there. That's really about it. Do you guys have any more questions, comments? learned more about, you know, everything. I should retitle this "Everything You Wanted to Know About InnoDB" and then some, and are still afraid to ask.